All right, we're going to talk about it looks like chi. It's actually called a chi-square test or a chi-square distribution, not the x-squared test. Just to clarify there. So we're going to look at a chi-square test, and this allows us to introduce a new distribution that we haven't seen before. So let me first talk about the purpose behind it. We use this whenever we're trying to look at counts of categorical data. So this is the first test that we'll look at that doesn't involve some sort of numerical. So we're not looking at means and standard deviations. Instead, we're looking at the counts of categories. Chi-square comes in three different flavors, three different types. We have what's called a goodness of fit or univariate test. We have an independence or bivariate, and a homogeneity. Let me say that one more time just to make sure we got that right. Homogeneity, which is univariate with two samples. Now, just kind of clarify real quick, the goodness of fit is when we have one variable and we're comparing the one variable to what we expect the one variable to be, and then independence and homogeneity are when we're dealing with two samples, and we'll talk about the characteristics behind those a little bit later. Alright, so chi-square distribution is a little bit different than a normal distribution in that it is based on degrees of freedom. So this is kind of reminiscent of t-scores and t-CDFs and that sort of thing. And as we increase the degrees of freedom, you'll notice that the curve actually starts to look somewhat symmetrical. And that actually will be true so it's a little more sample size we get, then we would approach it sort of a normal looking or bell-shaped curve. Although a lot of times with chi-square we're not going to have that many degrees of freedom. So one sort of idea to get across is that the different degrees of freedoms have different curves, and so the probabilities are going to change depending upon how many parameters or how many degrees of freedom there are. Generally, it is a skewed right distribution. Again, as you get higher degrees of freedoms, then your curve approaches more like a normal curve. Okay, so in order to do a chi-square process, we need to have some assumptions. So let's go through our checklist. SRS seems to be pretty standard with all of our distributions, that we are assuming the data was collected somewhat randomly. Then we have to have counts of categorical data, and what we expect to have in each category has to be at least one. So let me emphasize this because I'm going to try to trick you a little bit later in the presentation. In order for this to work, we have to have counts, not percentages, but counts of data. And then a third condition regarding sample size is that we have to have in at least category, in each category we have to have at least 5. So let me kind of back up a second, kind of make an observation here. In order for this process to work, after the SRS, we have to have, each category's got to have some value, so it's got to have at least one thing in it, but the sample size has to be large enough that we expect to see at least 5. So we typically combine these two conditions into a single condition, and we just say that we expect that there's at least 5. Again, this is expected, not observed. Okay. So what exactly is a chi-square? This is kind of reminiscent to t-scores and z-scores. We're taking the observed minus the expected, squaring it, and then divided by what we expected to see. And that's going to give us a sort of a measure of error. How far off are we from the actual expectation? And each observation is going to collect up a little bit of error, and then we're going to sum all those little errors together, and that number is going to represent our chi-square. Okay, so let's look at our first test. This is a goodness of fit. Again, univariate, meaning one variable. This is done to see how well what we observe fits with what we expect to see, and we're going to use our calculator to actually figure out the p-value. So once we type it in, then the calculator will kind of do all the number crunching underneath the hood for us. And again, degrees of freedom are the categories minus 1. Okay, that will change with later tests, so just be aware that I know degrees of freedom has always seemed to be sample size minus 1. This is categories minus 1. Okay, so when we are setting up a goodness of fit test, our sentences for the null, pretty straightforward. The proportions are equal. Of course, proportions of what, so we want to add some context to that. And then alternative is that we expect to see at least one proportion is not the same. Okay? And of course, context, context, context. All right. So let's take a look at our first example. Does your zodiac sign determine how successful you will be? Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. Is there sufficient evidence to claim that successful people are more likely to be born under some signs than others? Okay, so let me kind of clarify what we're seeing here. They looked at the birthdays of big CEOs and tried to see if there's some sort of pattern. Maybe the summer months have a little more advantage than other months. Is there any rhyme or reason to why when you were born dictates how successful you are in life? Okay, and now we're going to suspend common sense about this. Now, let's go ahead and take out our calculator and let's type in those numbers into list 1. Okay, so we're going to go to our list 1 and we're just going to input all of those numbers. So 23, 20, 18. Go ahead and pause the video and type in the numbers. I don't think you need to see me type in all these numbers, but go ahead and pause it, enter the numbers, and then catch back up with me. Okay, so now that I've got all these numbers typed in, let's kind of talk through what we would expect to see. If I think that honestly there is no difference between any month, then I would expect, generally speaking, that there be the same number of people born in each month. Okay. Well, I've got 256 total, so I'm going to take the 256 and I'm just going to divide that by 12 because I think each month should have that. So it's going to take a minute here to get that typed in. So if you want to pause the video again, I'm just going to type in 256 divided by 12 all through the whole list next to the corresponding number that it matches. Okay, so now that I got that typed in, now we're going to kind of go through the mechanics and check our assumptions and kind of make sure that we're satisfying all. So kind of keep these numbers handy. I'd even say write them off to the side somewhere so you can kind of follow along with me as we check the assumptions. Okay, so we talked about the 21.33 in each category. How many degrees of freedom are there? Well, how many categories do we have? We've got 12 signs, so 12 minus 1 would give us 11. So we expect there to be 11 degrees of freedom. Okay, so let's go through our assumption list and set everything else up. So our assumption is that we have a random sample, and it's stated in the problem. Our expected count is 21.33 for each category, so it's clearly greater than 5, so I need to make a sentence stating that. For our null and alternative, the proportions of what? Well, proportions of CEOs born under each sign are the same. And then alternative is that at least one proportion of CEOs born under each sign is different. Okay. So then what I'm going to do is I'm going to set that chi-square formula up we saw a second ago. And then I'm going to show you how we can get the calculator to generate all of these numbers for us. Okay, so starting with the first month, we saw 23, but we expected to see 21.3. So we subtract, square, and then divide. The second month was 20, set it up that way, and all the way up to 29. Now, that's kind of tedious to do by hand. So again, I'll show you a calculator menu for that. So let me do that. Okay, so here we are back at the calculator again. And let's go to our test menu. So hit stat and then arrow over to test. And then we're looking for something that says chi-square test, goodness of fit. So right there, I went up instead of down. But anyways, if you keep scrolling down, you should see something that looks like chi-square, GOF, goodness of fit. So mine it's D, but yours might be different. And then I'm going to hit enter, and it's going to ask me where did I put my observed. So by default, it's going to think it's list 1 and list 2, but you can override it if you have your data typed in different lists. So my observed is list 1, what I expect to see is list 2. Degrees of freedom, there are 11, and then I'm going to calculate that. So let me hit enter, and it gives me all that lovely information there, that the chi-square is 5, and the p-value is 0.926, so very boring p-value. So now we're going to write our conclusion based off that. Okay, so when we compare our p-value of 0.9265 with our alpha, yeah, there's really huge p-value. So we're saying that I get excited if it's less than 5% of the time, and I've got a sample that would show up about 93% of the time. So this is a very boring sample. This is what I would expect out in the real world. So clearly the p-value is greater than alpha. And so our conclusion would be, since p-value is greater than alpha, I fail to reject the null. There is not sufficient evidence to suggest that CEOs are born under some signs than others. In other words, birth doesn't matter, was what that data tended to show. Okay, let's do another example. A company says its premium mixture of nuts contains 10% Brazil nuts, 20% cashews, 20% almonds, 10% hazelnuts, and 40% peanuts. You buy a large can and separate the nuts. Upon weighing them, you find that there are 112 grams Brazil nuts, 183 grams of cashews, 207 grams of almonds, 71 of hazel, it's supposed to be of hazel, and 446 of peanuts. You wonder, as one should, whether your mix is significantly different from what the company advertises. Oh my, the shock, the horror. Did they lie about their nuts? Okay, so this is where we're going to do our goodness of fit test and see if what we observed is different than what we expect. Let's start by thinking about, have we satisfied our assumptions? Can we actually do a chi-square goodness of fit based on what we have? And think carefully about how your data is set up, and then what you would expect to have in your data. And the problem is, no, we don't. That's those percents. They gave us the percents of the categories instead of telling us how many counts they have. Now, that's an easy fix. We can just convert all those percents into counts, and then we would be able to do that. Okay.